Okay. Last time we discussed instruction cycle flowchart. So in that case, just let's have a quick look at that. We'll start the instruction flowchart with sequence counter to be 0. Then at time t0, we transfer the content or the transfer the address stored in PC to address register. Then at time t1, we fetch the instruction from memory. We increment the program counter by 1. Then at time t2, we decode the instruction using 12 to 14 bits of IR. Then we store 0 to 11 bits of IR to address register and 15th bit of IR to I flip-flop. Then we decide which type of instruction it is based on D7. The output, decoded output D7, we decide the type of instruction. If the value is 1, then it is register or IO. If value, now whichever it is, whether register or IO, it will be decided based on I flip-flop. So if I is 1, then it is IO, and at time T3, the instruction gets executed. Same way, if I value is 0, then it is register reference instruction. So again at time T3, this will get executed. Now D7, if D7 is 0, that means it will be memory reference instruction. Again, in that case, we have discussed if D0 is 0, that means it is memory reference instruction and it is end instruction. Then D1 is 1, then it is add instruction and so on. So D0 to D6. Then again, we are having two types of memory reference instruction, that is direct addressing and indirect addressing. So that is decided based on I. So if I value is 1, then it is indirect. And for indirect addressing, we always fetch address of address. So it is written by using statement AR equals to M of AR, address of address. So AR equals to M of AR, which executes at time T3, and then our instruction goes for the execution and we make SC to be 0. But if I value is 0, then it is direct instruction and we do not want any kind of effective address. It is always present in the instruction itself, effective address. So we do nothing at time T3 and then we go for the execution of the instruction. Always remember, any of the type of instruction is there, whether it is IO, register or memory, SC is becoming 0 once instruction gets executed. Now the thing is that in a program there are many instructions. There won't be any one instruction in a program. So when program starts, it starts executing the first instruction, then second, third, and so on. So in that case, the instruction gets executed, and correspondingly the cycle goes on until and unless HLT instruction is encountered in the program. This cycle goes on. So when HLT instruction is encountered, this cycle breaks and stops further execution of the instruction. So always remember this flowchart. This is the most important with respect to examination. Instruction cycle flowchart. Now please keep this in mind, this flowchart, because now we are going to discuss each and every instruction in detail. All the types, that is register reference, memory, and IO instructions. But before that, can anybody tell at what time I am talking of time, with respect to time I am talking, T0, T1, T2, T3. With respect to this instruction cycle flowchart, can anybody tell me at what time register reference instruction will be executed? Can anybody tell me? Yes, I'm waiting for the reply.
T3.
Sorry?
T3.
T3, but if you check out at time T3, IO also gets executed. I am talking specific of register. At what
When
time?
D7 is 0.
D7 0? You are near, but you spoke something incorrectly.
I मतलब वो क्या बोलते हैं register.
नहीं.
Register
Make
equals
it clear. Don't get confused. My question is, at what time register reference instructions will be executed? So one thing is correct at T3.
When register is 1.
Register is 1. Go in reverse pattern. See, one thing is very clear, at time T3 register reference will be executed. But if you check out at T3, I also get executed. But T3 is fine. So T3 should be 1. Can I say like this? T3 should be 1. One thing. What next? Go in reverse way. Bottom to top.
I should be 0.
Yes, exactly. I should be 0. So can I say T3 should be 1, I should be 0. Then
Register instruction.
Register
then
reference is execute.
no, no, no. Still something is missing.
SC is 0.
No.
0 assigned to
If we observe this flowchart carefully, then T0, T1, T2, these three time, this at time T0, T1 and T2, the operations which are occurring are common to all the types of instructions. One thing. At time T0, T1 and T2, whatever the operations or a part is executing, it is common for all types of instruction. Now the difference starts from here, that is D7. So my question was, at what time register reference instruction will be executed? So when T3 is 1, I is 0 and D7 is 1. Can I say like this?
Yes.
Yes.
So now speaking out correctly in sequence, when D7 is 1, I is 0 and T3 is 1, at that time register reference instruction will be executed. Am I correct?
Yes.
Now someone has to tell me at what time input output instruction will be executed.
When D7 is 1,
Correct?
I is 1,
Correct?
and T3 is 1.
Absolutely correct. So D7 1, I 1 and T3 1, at that time my IO instruction will be executed. Now can anybody define at what time memory reference instruction will be executed?
When D7 is 0,
Okay,
and I is 0 or 1,
okay,
and T3 is 1,
okay.
then it execute the memory reference.
But what about, okay, fine. Now you are not knowing one thing, that's why it is fine. But which memory reference instruction is executed? That how we can know. Whether it is add instruction, end instruction, LDA, STA, BUN, BSA. Can anybody state?
I 0 and 1, direct and indirect.
No, no, no. I'm talking of, say for example, I'm talking of end instruction. When can I say end instruction is executed? See, you forgot.
Register 1.
What value will be 1? Can I say D0 is 1? Then we can say it is memory end instruction.
Yes.
Same way, can I say D1 is 1? Then it is add instruction. Yes or no? So for memory reference instructions, we are having different value for, sorry, we get one from different outputs, D0 to D6. So this we'll be discussing this part. Sorry, just a minute. This part of memory reference we will be discussing in detail. Also, these two also we need to discuss it. But general format we got that if D7 is 1, I is 0 and T3 is 1, that means any of the register reference instruction will be executed. Any. We are in 12 register reference. Same way, if D7 is 1, I is 1 and T3 is 1, then IO will be executed. Did you get this general statement? All of you?
Yes.
So let's start in detail with register reference instruction. So one thing for register reference instruction, I have defined that D7 should be 1, I should be 0 and T3 should be 1, which I am stating over here. If I want to say I should be 0, that means I am saying I dash. Is it fine? What does this mean? What does this mean? That D7 should be 1, I dash means I dash should be 1 and T3 should be 1. And which I am denoting in general common way, that is R. Is it fine? So now the question arises, sir, this is common for all register reference instructions. What about specific instruction if we discuss? What about specific instruction, that is CLA, CLE, CMA, CME, CIR, CIL, SPA, SNA, SZA, SZE, HLT? How we can bifurcate of this? How we can bifurcate those instructions? We have already discussed into our previous part when we discussed types of instruction. You can remember. Do you remember this? We are changing 0 to 11 bits for register reference. So if this is bit 11, can I say? Bit 11 is 1. That means it is clear A, AC. Then if bit 10 is 1, then it is CLE, clear E. If bit 9 is 1, then we say CMA, complement accumulator. Yes or no? Bit 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 and 0. The same thing we need to discuss right now. But the main concern is what operation are getting occurred. So CLE occurs at what time? CLA occurs at what time? See, now I'm talking of time. It's already in front of you.
T3.
Array, time. CLA occurs at what time? Array, it is in front of you. CLA occurs at time D7, I dash, T3, D11. Got this? That means when D7 is 1, I is 0 or I dash is 1, T3 is 1 and bit 11 is 1. At that time CLA instruction will occur. Is it fine? Yes or no? Are you getting everyone?
Yes.
Please reply. If you don't get, please ask me immediately. Are you getting this?
Yes, sir.
Okay. Now just check out. CLA means what? Can I say CLA? Clear accumulator. So AC equals to 0. That means at time RB11, I am supposed to set the content of accumulator to be 0. So this is nothing but your complete, So this is nothing but your complete RTL notation. What is RTL? Register transfer language. That means at RB11, At RB11 time, AC will be 0. Control function. This is nothing but your control function. Is it fine? All of you. Should I move further?
Yes.
Sir.
Yes, sir.
Any doubts? Anyone have any doubts? Okay, fine. So what is our next instruction? Can I say CLE? Then in case of CLE, at what time CLE will occur? Now you have to tell me, or now you know. At what time CLE will occur? अरे सर लास्ट लेक्चर है, आप हमें परेशान कर रहे हो. यू आर आस्किंग द क्वेश्चंस, but it is for your understanding.
RB10.
Perfect. CLE means what we are supposed to do.
Clear E.
So can I say E equals to 0? I need to assign E to be 0. Is it fine?
Yes, sir.
Yes,
Next
sir.
instruction CMA. At what time can I say RB9? What we want to perform?
Complement.
Complement accumulator. How we can complement accumulator? AC equals to AC complement. Yes or no? Did you get this? Now see over here, what I wanted to actually explain is that we are going into detail of the instruction. See, earlier we were knowing just the description. Earlier we were knowing just the description, but now we are writing the actual operation occurring behind these instructions. Are you getting this? See, we are saying CLA means clear AC, but what actually occurs means we need to set accumulator content to 0. At what time? At time RB11. What is R? D7 should be 1, I dash should be 1, and T3 should be 1. Now, I dash should be 1 means I should be 0. So, we got our answer D7, I dash, T3. And which instruction out of this all register reference will be decided based on our bit stored in IR 0 to 11. So CLA RB11, CLE RB10, CMA RB9. Same way next is CME. At what time? RB8. What happens? E complement. So E equals to E complement. So complement E. Now next instruction is what we are having is CIR. Now this you have to explain me. CIR, circulate right, which occurs at RB7 time. But before teaching you this part, let us have an example. See this now. This is my E flip-flop and this is my AC register. The size of AC register is 16 bits. E flip-flop is 1 bit. What I am writing the content in AC register is 1 0 1 1 0 1 1 0. And my E flip-flop contains, let's say, 1. And I want to perform circulate right, CIR. What should be my output? Now over here, CIR means circulate, shift, right, AC and E both. Are you getting my point? AC and E both. That means this is my actually 0th bit. 1, 2, 3, 4, 5, 6, and 7. So instead of 16 bits, what I have taken an example is of 8 bits. So what should be my output of CIR? So basically CIR means logical shift right to hoga hi. That means all these bits should be shifted by one position like this. Yes or no? But the question arises, what about this 0? What about this 0? Do we need to discard it? No, it is not logical shift, it is circular shift. So this 0 need not to be discarded. So where this 0 will go? This 0 will be shifted to E flip-flop. And the content of E flip-flop, which we are having, will be shifted to this bit in our AC register, and this will be shifted to our E flip-flop. Did you get this in case of CIR? This is what is circular shift right using AC and E. Is everybody clear with this? All of you. Then let's understand the register transfer notation for CIR. See what I did earlier. I did shift right accumulator. I did. See, this is shift right accumulator. Huh? Just a minute. Yes. This is shift right accumulator. I already did. But along with that, I shifted the content of E flip-flop onto the AC's 15-bit. Okay, sorry, I had done the reverse process. I should not have written like this. Okay, fine. Now what I am doing, I am shifting this E. I am shifting this E to, can I say, AC's 7th bit. That means over here we are having 16-bit register, so I am writing 15 over here. So E value is shifted to AC's 15th bit, and the bit stored which was shifted, the AC's 0th bit was shifted to my E flip-flop. See, AC0 shifted to E flip-flop, which we are terming it to be circulate right, AC and E. Any doubts with this? All of you, any doubts with this? Anyone, please?
No, sir.
Is it clear,
No,
everyone?
sir.
Everyone?
Yes, sir.
Okay, fine. Then what about CIL then? Circulate right, which occurs at RB6.
RB6.
RB6. But say, for example, we take the same example. Sorry, 2, 1, and 0. Okay. Take the same example. What will be my output? I want to perform, just a minute, let us keep it as it is. Sorry. This is my CIR. Now I want to perform CIL on this data, what is available with me. On this accumulator, I want to perform CIL, means circulate shift left. So all these bits should be shifted onto the left hand side by one position. I have done this. Now, what about this first bit? What about this bit? And what about 0? Sir, we are getting confused. Okay, let me remove this. Just a minute. Let me remove this CIR. Okay, now you say. What about this now? How this will be occurring? Can I say shift left? That means this bit will be moving to this position, and this E flip-flop content will be moving to the last position. So can I write E is equals to AC of 0 and AC, yes, AC of, E is equals to AC of 15 and AC is equals to, AC of 0 equals to E. So this one goes to E flip-flop, and the 0 which was, this 0 goes to AC's 0th bit, and this goes to E flip-flop. This is your CIL. So let me show you that. See, it has changed. Shift left AC is to be performed, then AC's 0th bit will be assigned by E, and AC 15th bit will be copied to E flip-flop. Any doubts with this? All of you? The next instruction what we are having is INC, which occurs at RB5. It means increment accumulator by 1. So AC equals to AC plus 1. Very easy instruction. Next instruction what we are having is SPA, that is skip next instruction if AC is positive, which occurs at RB4. Now, how to skip the instruction? How we can write it in form of RTL, that is register transfer language. Skip next instruction if AC is positive. Now let me demonstrate the same part in this. Okay, now see this. There is a program written in assembly language. There is one program. Now program consists of 10 instructions. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 instructions are there in a program. Any 10. But out of this 10, fifth instruction written is SPA. It means when processor will execute this instruction, at that time, what processor will check? What processor will check? That whether accumulator is positive or not. If AC is positive, then skip next instruction. That means my direct control should go to 7th instruction instead of 6th instruction. So jump should take place. So how to do that jump? So my question is, whenever this instruction was getting executed, at that time, the address of 6th instruction will be stored in PC. You get this? Yes or no?
Yes, sir.
PC holds the address of the next instruction to be executed. तो उसके पास ये 6th instruction का address होगा. Now what happens over here is, say for example, this AC is positive at this point. That means next instruction is now not 6. What is next instruction now? If AC is positive, that means I need to skip this instruction. Then I need to go to 7. So can I say I need to shift my PC over here from here? So can I say can I increment my PC by 1? Yes or no? So can I say if AC is positive, say for example it is positive, then can I not say PC is to be incremented by 1? Did you get my point or not?
Yes, sir.
Why PC incremented by 1? Because we have to skip the next instruction. That means the sixth instruction was to be skipped off. That's why we incremented PC by 1. So that is what I have written. But how to check whether number is positive or negative? Can anybody state? How we can check that whether number in AC is positive or negative? Did you remember? It is electronic subject, as well as in our first chapter also I have discussed this point, whether number is positive or negative, how it is decided. I'm waiting. How you can decide whether number is positive or negative? In case
AC
of
is 0 or 1.
positive, negative, 0 or 1? You are somewhat near, but not AC completely. The most significant bit in the AC register, if it is 0, then it is positive. If it is 1, then it is negative. That means AC is positive or negative can be decided based on the 15th bit. If 15th bit of AC is 0, then we need to increment PC by 1. But if AC's 15th bit is 1, then number is negative. Are you getting my point? If it is 0, then positive. If it is 1, then negative. Over here, if AC's 15th bit is 0, then we need to skip the next instruction. Just check it out. Is it fine, everyone? Same way, what about SNA, which occurs at RB3? How will you write the RTL for this? How will you write RTL for this?
If AC 15 bit is 1,
Huh?
then PC is increment by 1.
Absolutely correct. Now the next instruction, SZA. Who will tell? Let me ask someone. Yes, Devang. Devang present? Devang correct.
Yes, sir.
Yes, Devang. Tell me what I should write over here. What should be my RTL? SZA. SZA means accumulator is 0. If
0.
accumulator is 0, then skip next instruction. Then what I should write?
If AC equals to 0,
Hmm.
then PC increment by 1.
Perfect. Absolutely correct. Is it fine, everyone? Yes. Thank you, Devang. Is it fine, everyone? Then same way SZE. If RB1, it occurs at RB1. If E is 0, then PC to be incremented by 1. Is it fine? And the last instruction for memory reference register reference is HLT, which occurs at RB0. Halt the computer means, say for example, I have kept in front of, suppose there are 10 instructions in my program. See, there are 10 instructions, sorry, in my program. And at the 10th instruction, I have written HLT. Means computer will understand that now program is over, no more further instructions are there. So what it will do, it need to break the instruction cycle. So there is one flip-flop named as S, which is termed as start-stop flip-flop. Start-stop flip-flop. So we are terming it to be S in general. So when a halt instruction occurs, at that time we need to set this start-stop flip-flop to be 0. Then we term this to be halt computer. Is it fine, everyone? In exam, it can be asked that explain the following instructions, and instructions will be written SPA, CIL, CIR. Each instruction for 1 mark, and you need to describe each and every RTL statements and the description and the timing at which these instructions occur. This complete CIR, if it has been asked into the exam, you need to explain that CIR is used to circulate, write SC and E flip-flop, and the RTL for the same, that is RB7, and you need to write this RTL statement. This consists of 1 mark. So similarly, it can be asked for 3 marks, 4 marks, 6 marks. We can ask 8 instructions even. Okay? Any doubts with register reference instruction? Any doubts with register reference instruction? All of you? Then can we start up with memory reference instruction? So the first memory reference instruction in front of us is AND instruction. What do you mean by AND? It is a memory reference instruction, means operand is stored in memory, which is to be ANDed with accumulator, and result is stored back onto accumulator. Please read the statement. AND instruction performs the AND logic operation onto the pair of bits in AC and the memory word specified by the effective address, and the result is stored back to AC. Any doubts with this? But sir, we need to write the RTL for this. But what you are thinking is not that easy. Let's discuss it. For that, we should know the common bus system again. Yes. This is our common bus system, which we discussed previously. Let me tell you one thing. We cannot perform any operation onto memory except write and read. Let me repeat my statement. We cannot perform any operation onto memory except read and write. So the question is, over here we are supposed to perform ending operation of accumulator content and the memory word. So we cannot apply this logic operation onto memory directly. So first and foremost thing for us is to bring this memory content, the word stored in memory, to some of these registers. In any of these registers we need to bring. So it's very obvious that in AC it will not be allowed because it is to be ended with AC. So we cannot move it to AC. Again, AR and PC, they are the registers which store address. So data from memory cannot be stored in AR or PC. Again, IR is meant for instructions. So we store instructions in IR. So only left out for us is DR, data register. That's why the name given is data register. Now, if you can check out why data register, because we want to perform ending operation. So that ending operation can be performed by adder and logic circuit. So you are knowing that DR is connected to adder and logic circuit. So first and foremost step for us is to shift the data from memory to DR register. And then the content of DR register is ended with AC register and result is stored back in AC register. Are you getting my point? So DR and AC, the result is stored back in AC. This is how it occurs. Get this point? So let us write the RTL for AND instruction. The first task is to transfer the content from memory to DR register. So it occurs at time D0, T4. Remember instruction cycle flowchart. Ending occurs at time D0 only. D0 should be 1. Nobody else should be 1. So at time D0, and D0 should be 1 and T4 should be 1, then at that time the memory content is transferred to data register first. Then at time D0, T5, D0 should be 1 and T5 should be 1. At that time the ending takes place. At that time ending takes place. See, AC and DR. Result is stored in AC. Is it fine? And again, if any of the instruction completes its execution, then sequence counter is made to be 0. This is what we did. Did you got the end instruction now? All of you?
Yes, sir.
Anyone have doubt?
No.
Then similar instruction we are having is add instruction. Add the content of memory word to accumulator and result is stored in accumulator. And if any of the carry is generated, Cout is generated, then that carry is to be stored in E flip-flop, which we term it to be extended accumulator. Fine. So again, the same thing. We cannot perform any operation onto memory except read and write. So again, the data is to be transferred to DR first. But see, the timing has changed. Timing has changed at time D1. In AND, it was D0. Over here, T1 should be 1 and T4 should be 1. Then the content of memory is transferred to DR. Then at D1, T5, AC is added with DR and result is stored in AC. If any of the extra carry is generated, that is Cout, that is to be stored in extended accumulator, that is E flip-flop. And sequence counter is made to be 0. That means we can say that instruction is executed completely. Any doubts with this? So AND instruction, D0 should be 1. Add instruction, D1 should be 1. And now you should be clear. See, add instruction requires 2 timing cycle to execute. Same way, AND instruction requires 2 timing cycle to complete. That's why I have not mentioned over here, if you can check out, see, that's why I have not mentioned the time. Sorry. See over here, that's why I have not mentioned the timing for memory reference, because in memory reference it is not fixed that it will be completed within one timing cycle. It requires more timing cycles, which where I had shown you the example that in our AND and add it requires 2 timing cycle. Same way in add also 2 timing cycle. It varies. In some instruction it requires 1, in some instruction it requires 2, in some instruction even it requires 3 timing cycles. Okay, any doubts with this? So today we stop here. Fine. Next time we'll be discussing further with the other memory reference instructions. Fine, but do be careful that all these instructions can be asked into the examination. Fine, all of you fine with this? So today we stop here. Let me take the attendance. Roll number 109. Absent. 180. Absent. 222.
Yes, sir.
41.
Yes, sir.
68.
Yes, sir.
69.
Yes, sir.
70.
Yes, sir.
71. 71. 71 absent. 73.
Yes, sir.
74.
Yes, sir.
75.
Yes, sir.
76.
Present, sir.
77.
Yes, sir.
78.
Present, sir.
79.
Present, sir.
80.
Present, sir.
81.
Yes, sir.
82. 82. Absent. 83.
Yes, sir.
84. 84. Absent. 85.
Yes, sir.
86.
Present, sir.
87.
Yes, sir.
88.
Present, sir.
89.
Present, sir.
90.
Present, sir.
91.
Yes, sir.
92. 92. Absent. 93.
Yes, sir.
95.
Present, sir.
99.
Yes, sir.
100.
Yes, sir.
101. 101. Absent. 102.
Yes, sir. Present.
103. Sorry, 105.
Yes, sir.
106.
Yes, sir.
108.
Present, sir.
109. 109. Absent. 111.
Present, sir.
112. 112. Absent. 130.
Present, sir.
133.
Present, sir.
150. 150.
Present, sir. Present,
155.
Present, sir.
D2 D1.
Present, sir.
2.
Present, sir.
3.
Present, sir.
4.
Present, sir.
5.
Present.
6.
Present, sir.
7.
Present.
8.
Present.
9.
Present, sir.
10.
Present, sir.
11.
Present, sir.
12. 12. 12 absent. 13. 13 absent. 14. 14 absent. 15. 15 absent. 16.
Present, sir.
17, 18, 18, 18, absent. 19,
Present, sir.
20,
Present, sir.
21,
Present, sir.
22,
Present, sir.
24,
Present, sir.
20, 25,
Present, sir.
41, 41,
Sir, 18 present.
sir.
42, 42,
41 present.
41 present, 42, 42 absent, 44, 44 absent, 45, 45,
sir. 45.
46,
Present, sir.
47, 47 absent, 48,
47 present, sir.
Present.
40
47 present, 48,
present, sir.
49, 49, 49 absent, 50.
Yes, sir.
Okay. D2D 18 present. Okay. Anyone else left out? Okay,
Yes, sir.
fine.
C92.
Sorry?
CE92.
92. Yes, okay, fine. Anyone left out? Thank you, all of you.